Foundation models, GPT, Claude, Gemini, they are genuinely remarkable. They can write code for you, they can summarize things for you, they can reason through problems. We have been using this for almost 3 years now, and I have been using this. It's a great piece of technology. We all know that. But there is always a but. Talking about a hospital, hospitals, their problem is not just general intelligence. They speak in a different language altogether. They speak in terms of ICD codes, they speak in terms of triage language, clinical note summary. These are high stake, precise tasks, which if you get the ICD code wrong, then it could be a problem with the insurance claim itself. Foundation models, they can generally speak about everything, but model trained on such ICD codes can understand when a hospital is say something like this: patient complaining of shortness of breath with a history of congestive heart failures. Now it's been trained on thousands of such ICD codes. Now these models just speak the language of the problem. And on top of that, ask yourself this question: do you want the patient's records to be going out of the hospital infrastructure? Yes, the cost itself adds up when you're doing thousands and thousands and thousands of queries per day because you're paying per token. And this is where the map flips and teams they start thinking about using open source instead of foundation models. Or think of the law firm doing the contract review, or the bank doing the fraud narrative generation, or the manufacturer doing the faulty equipment diagnosis. Now, all these are high stake tasks which are very narrow focused. Now, a foundation model can do a lot about everything, but a domain specific model can give you the precise answer what is required. Nothing more, nothing less. That's the world I want to explore in this video series. Not instead of a foundation model, but alongside with it, and when to use what, and how to build that open source stack that gives you that choice. So, this is what the series is about. I want to go deep into the world of open source, talk about domain specific small language model. We're going to take slow steps. We're going to start with RAG agents. Then we're going to look at some other concepts like fine tuning, quantization, LoRa, caching, Onyx, and see how they all fit together when we run these models in production. We're going to look at some actual numbers running some notebooks and see how they all fit together. Starting with a simple RAG application, we're going to embed some Wikipedia articles on the history of AI. Our embedding model is going to be all MPNet base v2 from sentence transformers. The vector database is going to be LanceDB, which we're going to run it locally. The model is going to be Qwen 2.5 3 billion parameters, which we're going to run in GGUF format. We're going to first run this in a CPU hardware and then run that in a GPU hardware and see if there is a difference in the speed itself. And then we're going to try that with a slightly bigger model. So stay tuned and let's open the notebook. So before I show you the notebook running, I want you to give you this mental model so that it clicks. Otherwise, it will feel like we are talking about slow versus fast thing, which is not the point. Now, every time a language model generates a next token, it performs a huge number of floating point operations, mostly matrix multiplications across the model layers. The CPU can do a little bit of parallel work with this limited amount of cores, but when it comes to GPU with thousands of the smaller cores, it can do a lot of this parallel processing more efficiently. And that's the difference. It's not magic, it's parallelism. And here's the number that matters. Now think about a CPU, and if for the demo we are using this model ran 2.5 3 billion parameters. Now, if you're using this model for a CPU, it will generate 3 tokens per second. Now, if you are using a T4 GPU, then the same model would generate 60 tokens per second. Now, that's like a huge difference. Now, think about it, for a 200 token answer, a CPU with a 3 seconds, or CPU would take close to 60 seconds, and GPU would take close to 3 seconds. Same model, same code. And that's just one line change. But here is the thing you have to mark, like, why would you want to run on a CPU after all? Because 2 years ago you couldn't even run on a CPU. The technology has advanced so much that you can run this smaller models even on a CPU, although it may seem like a little bit slower. And the answer to that is quantization. Full precision. This model, the same model which we are talking about, is 12 gigabytes. Now you can load that into RAM while using a CPU. Quantization is a process where it takes all these weights, each numbers in the model, from 32 bits down to 4 bits. The model now becomes 1.8 gigabytes. You lose a tiny fraction of the accuracy when you do this process, but you have the ability to run this on any machine. Now, let me also talk about GGUF file format. Now, this is a file format that packages those quantized weights so llama.cpp can load and run this efficiently. Now, that's the whole trick. And once you like really understand this whole math, like the table what I'm going to show right next to uh, me is going to make a lot of sense, which what I'm talking about. So, looking at the model size table, it's evidently clear that as the model size becomes bigger, you either need like a better hardware or you need to perform some sort of quantization to make it fit. But the decision you're making every time is a trade off. How much quality are you willing to trade to keep the hardware cost reasonable? Now, here is where it gets interesting. Once you factor in the fine tuning, a domain specific 7 billion parameter model can outperform a general 70 billion parameter model. You don't need the biggest model, you just need the right model for your use case. Now, let's see that in action. I'll run a couple of notebooks so you can exactly see what is happening under the hood. So, I have two notebooks, one for CPU and one for GPU. The content is exactly same. We build a knowledge base from Wikipedia articles on the history of AI. Then we use the embedding models as all MPNet base V2 from sentence transformer. We use the vector database as LanceDB and the model as Qwen 2.5 3 billion instruct. Now for the CPU, what we do is we use something called a GGUF format, which allows it to run on the CPU. For the GPU, we have to do three changes, and I'm going to show those three changes. The first one is change the runtime required to T4 GPU. So go to runtime, change the runtime type, and select T4 GPU. The second important thing you need to do is you need to install the CUDA version of the llama.cpp Python instead of the default version of it. And last but not least, while loading the models, you have to set the NGPU layers is equal to 1, which allows it to run all layers on the GPU. Okay, so I'm going to kick off both the notebooks now and pause the video. The setup and inference will take a few minutes and I'll come back when both runs are complete. So both runs are complete. Now let me show you the output. Now quick note before we look. Now this is not a CPU versus GPU benchmark difference. We are demonstrating two different things. One is we are loading an entire quantized model on a CPU, and then we are showing that the same model we are running on a GPU, the speed significantly improves. Starting with the CPU, you can see the responses. Responses are mostly in minutes. And again, you're loading a 3 billion parameter model entirely on a CPU, and you're getting grounded, accurate responses from the model, which is pretty cool. Now let's look at the GPU. The GPU, if you look at it, it's in seconds, and that's kind of like obvious. So here is the takeaway, that we are not saying that it's CPU versus GPU. Now, if you want to run local inference like in your laptop, then you can opt for a CPU, and if you want speed, you can opt for a GPU. And that's the entire difference. The model and the pipeline in both the cases did not change. So that's a wrap on video one. So we built a complete RAG pipeline from scratch. We used open source model. We used local vector database. So no API keys, no token usage. And we ran it on the CPU and GPU, and you saw the trade-off. Now this is just a start. Next video, we're going to look at low rank adaptation for LLMs, also called as LoRa. Now the notebook for this video, it's in the description. So run it yourself, swap your own documents, change the model, and that's how real learning happens. Now, if you like this video, please subscribe. But until then, see you in the next video. Bye.